Hello everyone, my name is Maxence. I'm a PhD student from the University of Grenoble in France. I will present you our paper, AMLSI, a novel and accurate action model learning algorithm. I will begin by a little introduction about automated planning. Our automated planning is a field of artificial intelligence which develops planners to solve planning problems. A planner takes as input a planning problem and a planning domain and returns a plan, applying based on an action sequence. The planning domain is a set of preconditional effects of all actions in the planning problem. An encoding real-world system as PDDL domains is generally accepted as difficult, tedious, and error-prone. The reason is that the experts of the system to model are not always PDDL experts, and vice versa. This paper focuses on the following issue: how to automatically learn accurate planning domains. To overcome this issue, the planning community developed specific algorithms to generate PDDL domains and avoid PDDL expertise. For example, we can cite ARMS, LOCM, EXPO, etc. Some of these algorithms take as input plan traces, so plan resolving planning problems. But acquiring this kind of training data is difficult and costly for a real-world system. Another problem is that these algorithms are generally tested using syntactical measures, and some of these algorithms are not accurate. In other words, these algorithms are not able to learn domains able to resolve new planning problems. Now I will present our approach, AMLSI. The key idea of the AMLSI is that the real-world systems are implicitly related on state machines, and we can query the state machine and retro-engineer them into PDDL domains. So the AMLSI approach takes as input the set of action and proposition of the real-world systems and returns an accurate PDDL domain. AMLSI is divided into phases, a querying phase and a learning phase. The idea of the querying phase is to query the state machine with action sequences randomly generated, and the state machine returns observations. The observations being the intermediate states. So I will now present the learning phase. The learning phase takes as input sample built during the querying phase. This sample contains positive and negative example. A positive example is a feasible action sequence, and a negative example is an unfeasible action sequence. And the learning phase returns a PDDL domain, and more precisely, a strip-like domain including static and negative preconditions. The learning phase is divided in 3 steps: a grammar induction step allowing to retrieve the state machine related to the system. Then AMLSI generates a PDDL domain from the state machine, and finally AMLSI refines the PDDL domain. A planning problem can be represented as a regular grammar. Here we have an example of regular grammar representing a problem from the block-sort domain. The interest of regular grammar induction is that it is a well-defined problem with implicit algorithm like RPNE. Then, represented our problem as a regular grammar allows us to compress observation in mappings. This mapping says that in node 0, for instance, before the execution of the action pickup of A, for example, I always see this proposition at true and always see this proposition at false, etc. Then, after learning the regular grammar, AMLSI generates preconditions and effects. To learn the preconditions of an action O, we find all propositions that are always present in all nodes where action A, instantiating O, is feasible. For instance, holding X is a precondition of pat down if and only if holding A is present in node 1 and holding B is present in node 2. Then, generate effects is similar. Not holding X is an effect of pat down if and only if holding A is present in node 1 and absent in node 0, and if holding B is present in node 2 and absent in node 0. Then we have a convergence refinement step allowing to retrieve all effects and preconditions lost due to the fact that observations are partial and noisy. Effect refinement allows to ensure that all transitions in the grammar are feasible. The precondition refinement is just a syntactical refinement for each negative effect with a corresponding precondition. Finally, the taboo search allows to deal with noise. The fitness score of the taboo search is composed of 4 components. The first component checks that AMLSI encode all preconditions and only real preconditions. The second one checks that we encode all effects and only real effects. The third one checks that the domain can generate all positive examples. And the last one checks that the domain does not regenerate any negative examples. Now, we'll present our experimentation. To test AMLSI, we use 4 metrics: error rate for preconditional effects, the syntactical distance, and the most important, the accuracy. Error rate and the syntactical distance are syntactical measure, and the accuracy measures the ability of the learned domain to resolve new problem. We compare AMLSI with the LSNO algorithm, which is the algorithm with the most similar inputs. And we test AMLSI with 4 different experimental scenarios with complete and partial observation, with noiseless and noisy observation. When observations are complete, we are always able to plan with high accuracy, whatever the level of noise. And we can see that AMLSI outperforms LSNO. When observations are partial, AMLSI keeps an high accuracy when observations are noiseless. And when observations are noisy, learned domains are always able to resolve the majority of planning problems. Finally, we can note that even with partial observations, AMLSI outperforms LSNO. To conclude, AMLSI has good results with high level of observability and it's robust to noise, so AMLSI is an accurate algorithm to learn planning domain. So in this version of the algorithm, we are able to learn planning domains with partial observation, with deterministic and non-deterministic effects in the observation. So as future works, we plan to develop an incremental extension for AMLSI and extend the expressivity of the learned domains as temporal or hierarchical domains, for example. Thank you for your attention.